All right, so we were making the point 3D class. Does anyone remember if we finished writing that one? So here's the point 3D class. Oh, let me fix the lighting. There, it's a little better. So the whole point of the point 3D class was to contain all the information about the point in space for the sphere. The sphere class will have a point 3D instead of having an XYZ coordinate. Obviously, the point 3D has the XYZ coordinate, but the sphere won't have it directly. And this will allow us to offload the work of the point, of all the point stuff in the sphere class. We can offload the work to the point 3D class. And this is perhaps better too, because what if we want other three-dimensional shapes that need points to help be defined? So if we can have one class to keep track of all the point stuff, that's awesome. So here was the constructor. All it is an XYZ coordinate. It doesn't need a radius because this is just the definition of some point in some three-dimensional space. So it's got x, y, z. We just assign the attributes. Remember, self.x is the attribute x. Just x, that's the parameter x here. They're entirely independent except for the fact that they have the same value as a consequence by line 10. Oop. Similarly for y and z. So here is the calculate the distance from point. This is exactly the same as it was from the sphere, except we're taking it out of the sphere and we're putting it into the point 3D class. So we ask a point now, how far away are you from some other point in three-dimensional space? And then equality, what does it mean for 2 points to be equal? I don't know about you, but an intuitive option would be if they are the same point. If they have the same x, y, z coordinate. A repr, let's just follow that pattern of name of the class, parenthesis, and then each attribute within parentheses. The repr doesn't have to be this. It could be whatever you want. It depends on what the object is. For these plain old Python classes, they're just very simple. This is pretty typical. But think of the list, right? A list, when you print out a list, you see something very different. You don't see list, open parenthesis, its length, and some other attributes. No, you see the actual data in the list, because that's helpful. Here, there's nothing particularly fancy or special that we need, so we'll just say the name of the class followed by its attribute values. Yes?
Can you explain the use of the curly brackets in the return statement?
Right here? Yeah. This is just part of the F string. So let's just go do an example real quick. So if I have some variable a equals 55, this is entirely unrelated to the point 3D, right? Remember how if I wanted to print something out, or if I wanted to make a string, b equals is a plus right? That's how we would do it. And there's nothing wrong with this, but there's some syntactic sugar to make this a little nicer. It's called F strings. All you do is you put an F in front of it, and then instead of doing that, you can actually write it in line, like that. Oop, nope, not like that, not like that. Come on. Okay. The squiggles, the braces don't get rendered, right? They're not included. It's just how I say, here's the value. And that the big key difference here is I put F in front. I assume the F means format. I really don't actually know. You can even I'm trying to remember how to do this. 0.2f? Yeah, there we go. You can even, there's other fancy stuff you can do where you're like, ah, well, it's a float, but I only want 1 decimal place. You can even do this too, where it's like padded, where it's at least this many characters long. It's all this extra stuff for formatting. Don't try to memorize this stuff. Just when you need it, you look it up. That's what I do. So that's all the brace is. So this is just the F string. X, and then tell me what the X is, the Y is, and the Z. It's just a little easier, a little nicer to look at. Now if we go up here, we can see the point3D class. So we've got the, here, let's get rid of the doc strings to shorten it. There. All right, it's just the attribute, or the constructor, distance from point, and then equals and repr. There. That's what we've got. And now we can make point3D objects. There. All right. And we can check, well, what's the distance? Should be 0. What did I point? There. We're using the methods. We use the constructor. Of course, we never call it directly. We call it indirectly. We're using, I'm printing it out, which means we're indirectly calling repr, which is, that's why we see point3D, x is 0, y is 1, z is 2. We're using the EQ with this, because again, we don't call it directly. We use equals equals, and that's how we call EQ. And then finally, the distance from point. I'm asking 2 equal points, how far apart are they from one another? Their distance better be 0. It's 0, so that's good. So there we go. There's our point3D class. But of course, so any questions up until now? So of course, this doesn't, we now need to go and update the sphere class. The sphere class before stored its x, y, z value, and it calculated its Euclidean distance on its own. But now we don't want to do that. We want to create a sphere, and we want the sphere to have a point3D object, and we also want to update everything that would require any access to the x, y, z values. We got to go through the sphere to do that. So first of all, there. Here's the new constructor. Let me see, do I have, is it a little different here? Yeah. Here's the new constructor. It still takes a radius, but now instead of taking an x, y, z, it takes a point3D object. I called it center point because that's what it is. And I assigned that one attribute, center point. Now, of course, the attribute center point is a point3D, which means it has an x, y, z value. But anyways, diameter, well, that's the same. Surface area, it's the same. Volume, that's the same. That doesn't change. Now, distance between centers, well, now I don't call distance between centers. No. I say, hey, self.centerPoint, that's the center. That's a point3D object. Dot distance from point other.centerPoint. So now this class isn't doing the calculation, because the calculation for the distance between points is within the point 3D class. So we get self's center point, which is a point 3D, and I ask it, how far away are you from the other's center point? So the work isn't being done on spheres. No, the work is being done on center points that spheres have as attributes. Questions about this now? Distance between edges, well, I can still call distance between centers now. I can still call mine because that just asks the center points. I can do the overlap. That doesn't need to change. And now the equals is a little different. Now, instead of checking, is the x, y, z the same between the two? No, I don't care. That's not the sphere's problem. The sphere only cares, are the center points equal? And as far as the sphere's concerned, the sphere doesn't actually need to know what it means for center points to be equal. It doesn't need to know the details. All it needs to do is be able to ask a center point, hey, are you equal to another one? And that's what this is doing. We're seeing, okay, is the radius the same? Yeah, okay, that makes sense. And then we say, hey, are the center points equal? Which is interesting, because the sphere's equal. In order for it to know if it is in fact equal to another sphere, it needs to ask its center point if its center point is equal. And where did we define what it means for center points to be equal? Right there. So the sphere's equal calls the point 3D's equal, which is pretty neat. And if you don't believe me, you can always just do a quick little check here. Oops. They're equal, and you'll see it said true. Why? Well, this equal didn't do it, but when I ask the center point if it's equal, it goes and it checks, and it runs this code, which said first thing you do is you print out high, which is of course silly, but we see that it ran. And give me 1 second. And look at the repr. Take a second and look at this repr and see if, does that make sense to you? No? Well, we see sphere, because I'm asking the sphere, what's your repr? So we see the sphere, and then it's, okay, the first attribute is center point. And what do? Well, I say, print, give me the string representation of the center point. And where's that defined? Within the center, or within the point 3D class, which is point 3D, x is this, y is this, z is that. So we get this whole string to go right there, comma, radius. We get that whole string to go right there. You had a question?
Yeah, how far can you nest these?
As far as you want. You could do this forever. That doesn't mean you should, but you could. There might be some design limit that maybe it exists at like 128, I don't know. Maybe there is, but for all intents and purposes, let's say there isn't. But maybe there is. I really don't think there is, though. Yeah. Any questions about that? When in doubt, what does the code say? If you're like, whoa, that doesn't make sense. No, it does. You're just trying to skip some steps. Slow down. What does the code say? The code will tell you. Okay, methods, yeah, they stay the same. Sphere, repr. Hold on a second here. Oh, shoot. Cool. Okay, any last questions before I move on to the next topic? Yes?
Would that be considered easy to follow, or are there ways that you would want to clean that up too?
I would say it's still easy to follow because you could follow it one step at a time. Now, I don't mean trivial. I don't mean the fact that you're not going to be like, okay, where does this? Oh, well, that's this. What's the type? Okay, I need to go look at that class's type. But that's the name of the game here, right? Is you just kind of have to follow that stuff around. When in doubt, what is the type of that object and what was the method you called on it? The hardest part here is being aware that, okay, in this case, those magic methods were called. But consider here, with the distance between centers, if I ask a sphere, how far apart are you from another sphere? The sphere needs to ask its center point 3D object, how far apart it is. So it's like, if he's a point 3D and you're a sphere, and I ask, how far apart are you from that sphere? You're going to say, well, I'll get back to you. How far apart are you from their point? And then they tell you, and then you tell me. And we could play this game forever. Yeah. Other questions? All right, so, here's something I want to point out, is you might have noticed, can you see reasonably well at this size at the back? Yeah. You may have noticed that the sphere object took a point 3D object for like the parameters. When you create it, you have to give it an attribute that is, or an argument that is a whole point 3D object. But you might wonder, you might think to yourself, well, why not just have like x, y, z given, and then have this create right? So give the sphere the x, y, z coordinate, and then have the sphere create an instance of a point 3D on its own. And there's nothing wrong with that. There really isn't. But now by doing it this way, we are forcing this, like, look, the sphere class definitely does still need a point 3D, whether it's like this, oops, or it's like that. So it's still needed. But when the class has to create an instance on its own, that class becomes so hardly dependent on the other one, where if you kind of take its creation out, suddenly, it still needs the point 3D object, but I don't know. It's usually a little, in my opinion, I think it's a little nicer to do it this way, where you create the point before, and then you give the point to the constructor, as opposed to giving the constructor the 3 values so it goes creates its own point. Because what happens if I go and I change, what if a point 3D needs a couple more attributes in the future? Suddenly I now need to go update this constructor, where if I add more attributes elsewhere, I still only need to give this a point 3D. So there is some design advantage to doing it this way, but be aware that it's not wrong to do it the other way. It could become problematic in the future for your code if it grows. Okay, last chance for questions before we move on to something a little bit different. Okay, so at this point, look, if I wanted to make a sphere object, if I wanted to test, the diameter of a sphere, right? I need to make a sphere. I need to say, okay, hold on, I need a point equals a point 3D 0, 0, 0, yeah, and then A equals what am I doing wrong here? Right? This is what I'm testing. But if I want to run one test on diameter, I need to create a point 3D object, I need to make a sphere, and then I need to call the function, or the method. Now you could say, well, you don't really need to do it this way. You just, you can create it in line like that. Right? You could do it like that. Yeah, you're right, but the point I'm making is I still need to make a point 3D object, which I can then give to a sphere, to make a sphere object that I can then ask what its diameter is. Where before, when you were writing a function, all you had to do was say diameter, like assert diameter equals whatever, right? That's all you had to do. Now there's more setup. And you're like, well, 2 lines of code, what's the big deal? You're right, but it's only going to get worse from here in terms of how much setup. And you got to remember, that's for one test. What if I want to test the sphere where the diameter should be 0? What if it's really big? I need to do, there's a lot of like repeating here. There's a lot of overhead now associated with a single simple assert test, which is problematic. It really is going to become difficult. It's harder to manage. The assert tests, like if this is just to test diameter once, it's going to be huge. And there's a lot, it's going to be hard to look at. It's going to be hard to know what each line is actually testing without taking a few seconds to look at it. There's a lot going on. And it'll do the trick. The assert tests will work, but they're not, pardon me, they're getting hard to work with. They are limited in how flexible they are. So now we're going to switch to using something a little different for writing our tests. We're going to be using a testing framework called unit tests that's built into Python. It's great. This really is what we want to use. This really is what we should have been using since day one, but the problem is it requires you to know quite a bit before we can actually use it, right? So I couldn't throw you too much into the deep end. Don't get me wrong, there's still going to be a bit of stuff that I'm going to have to show you that you're going to have to say, like, I'm going to have to tell you, okay, it's the magic code, I'm sorry, deal with it. But it's far less now than it would have been if this was like a month and a half ago. But we are going to switch to unit testing. And this is a much, much better way to test for a lot of reasons. Yeah, okay. Yeah, there's another one, really popular one for Python called PyTest, but we're using unit test. Unit test, it gives us a lot more, like before we were just saying assert something. Well, unit test provides a lot more different types of asserts. I'll show you a few. It facilitates automated testing a little bit better. You can have shared setup and like tear down code, like shutdown methods if you need them. You can have subtests if you have one method you want to test multiple times. We'll see it. And at the end of the day, it's going to give us much better reporting on the results of your tests. Remember before with the assert tests, if they all passed, Python didn't say anything. And you'd go like, okay, I guess I'm happy. Where now, with using unit tests, when you hit run, it'll tell you test passed. If a test failed, all Python would say with the old assert tests were just like assert failed, here. Now it'll say, okay, assert test failed, got this, expected this. So there's a little bit more to it. It's a lot nicer and better to work with. I'm not going to be able to give you an exhaustive, we could have a whole course on unit test. So I'm not going to be able to give you an exhaustive demonstration of everything you can do with unit test. All I'm going to be able to do is show you where to start, and then you can go and play as you go. Fortunately, in spite of the added complexity, which really there isn't, it's not too bad at all. the spirit of what we're doing is the same. The idea, like what we were achieving with the assert test, is exactly what we're going to achieve with the unit test, except now we have a nicer way to do it. With that niceness comes a little bit of extra work, but you'll see it's not bad. There we go. So here's how we start our unit test. And in fact, here's a bunch right here. I'm just going to get rid of all these for now. It's not going to work. I need to pass. There. This is how we start. We have to import the thing called unit test. That's what we're going to use. And then we create a new class. Just like any other class, it's going to have that camel case naming. And it starts with an uppercase. But we always add the word test at the end. So this is a unit test class for the sphere class. So sphere test. If we were doing one for point 3D, it would say point 3D test. If we were doing one for circle, it would say circle test. That's what we're going to call it. But there is something different here that we haven't seen before. We see parentheses next to the name of the class. We never had to do that before. Never had we had parentheses next to the name of the class. Without getting too much into the weeds on what this means it means we're inheriting from some other existing class called test case. Basically what it means is we're making test cases specialized for the sphere. That's really what it means. And when we do this, it gives us a bunch of existing methods that we can use, that we will see. We'll be able to use methods on self that we didn't write because they were in the test case class or some above class. So yeah, as a convention, we call our test classes some class test, where some class is the name of the class we're testing and test is test. So this is the sphere class, so it's sphere test. Also notice unit test.test case. Yeah. Any questions so far? The biggest crazy thing is, well, we need import unit test. We call it test, that's convention, but really it's this. This is the big thing here. That's required for this to work. Questions? So, here's 2 unit tests I wrote, and let's talk about them. First, this is 2 unit tests. There are a few key things here I want you to notice. These test methods are methods. They belong to this class. So these are methods. That's why they require the self parameter there. And each method's name starts with test underscore. This isn't a convention, this is required. Your unit tests need to be test underscore whatever. And then the name that follows the underscore after test, so like test underscore is like the prefix, the name is as descriptive as possible. The name of the method should make clear what the test is testing. And the reason for this is later when I hit run on these unit tests and one fails, if I look at the name of the test and it says sphere center point returns correct point 3D failed, I go, oh, there's an issue with the sphere returning the center point. The name of the method tells you what's wrong. In fact, here's a convention. So it's required that you say test underscore. But the convention we're going to follow is, now here with the constructors, it's a little funny. But the convention is going to be, let me see down here. I'll get to the convention in a moment where it'll make more sense. Because with the constructors, the convention's kind of hard to see. Okay, yeah. We are making use of, no, here. I create a sphere. Okay. Def. Test sphere center point returns correct center point. Or correct point 3D. I create some sphere with some arbitrary point 3D object there. Give me 1 second. And then I say self.assert equal. Assert equal is a method that's written in the test case class that we get for free because we inherited from it. So we say self.assert equal what I expect to get, and then sphere.centerPoint. When I say sphere.centerPoint, I better get this back. If I don't get this back, meaning it's like if it's not equal to this, whatever I get back, something went wrong. You had a question?
I was just going to ask about like the name of that test. Like, I know it's all snake case, but like the very end, the E there's capital.
Oh, that's just because it's, you mean here? It's just because the name of the class is point3D. I could have said lowercase d, doesn't really matter here. Interesting observation, nevertheless. The next test is the radius. Create the sphere, self-assert equal. I'm expecting to get back 11 when I say sphere. What's your radius? If I don't get back 11, something went wrong. The constructor's clearly broken. Any questions now? Okay. Where you, yeah, self.assert equal. You'll notice that there are a lot more. What do we got? Assert almost equal, assert count equal, assert dict contains subset, assert dict equal, assert equals, assert false, assert greater equal, assert in, assert is. There is a lot. A lot of them are pretty niche. The most common ones are going to be things like assert true, assert equals, assert false. Those are the ones you're most commonly going to see, but there are a lot available that you use when you need them. Another thing you might ask yourself at this point is, you know, why not do this? Oops. Why not do something like this? Test sphere attributes. Right? Why not combine those tests? It's kind of silly to have them separate. No, it's brilliant to have them separate. Because if that top test fails, one of two things went wrong. Either the center point thing failed, or the radius failed. Having it this way, if the top one fails, I know what failed. Each unit test should only test one thing. There is an exception when we talk about subtests, but it's because it kind of is still only testing one thing that we'll see shortly. But each unit test, really you only want to see one assert in there. Because if something fails, we want to know why exactly it failed. As soon as you start having more than one thing, you're not going to be able to tell. It's going to be a lot harder to tell at least. Yeah, okay, yeah, each test tests one thing. And you'll notice that each test is self-contained, right? All the setup code for this test is in here. It's in its own method. It's nice. It's clean. It's easier for me to look at a test and know what it's testing. I just read the method name. Where before, if I'm looking at a wall of assert tests, I'm going to get lost. It's going to be hairy. It's going to be hard to see. So this right here is the start of how we're going to be doing unit tests. Questions, questions, questions. So other than those points, so far not much. Yeah, okay, the basic idea of how we write tests is the same. The only difference is the syntax. Okay. So here's a few more. Let's do the equals and repr. Great. So we're adding 4 more tests. So I'm testing equals. Test equals on equal spheres returns true. Great. So I create 2 sphere objects that should be equal, and then I say self.assert equal, make sure that they are in fact equal. Now, one interesting thing here is when I call assert equal, it actually has to make use of the sphere class's equals method. Like, it doesn't know what it means for 2 spheres to be 2 spheres to be equal unless I wrote the equals method for the spheres. Otherwise, it's the default one. And who remembers what default equality is? No one remembers? Exactly. If they literally, usually what we would use, the word we use in that case is. If you have aliases, if they are literally the exact same object. So here, that would be the case, if it's literally the same thing. In fact, by the way, there is a assert is, if you did want to check that you did have 2 aliases, or is not, if you want to ensure that they are not aliases, for example. So there we go, assert equals. Create 2 spheres that should not be equal. All right, great. Test equal on sphere and string. The choice to compare it to a string here is just a case of I want to compare a sphere to something that's not a sphere and ensure that I'm not getting true back. Well, there we go. They definitely shouldn't be equal. A sphere and a string should not be equal. And then test repr, arbitrary sphere, returns correct string. So if this is the sphere and I get the string of it, I better get this. If I don't, something went wrong. Okay. Yeah, we assert not equal, assert equal. There's a lot that we could use. Assert true, assert false. So here's what I was going to say a moment ago, where it was kind of hard to see with the constructor. Here is the convention you're all going to follow. It's required, again, it's required that each test starts with the name test underscore. It must, otherwise it won't work. But the pattern we're going to follow is method we're testing, under which case, and what we expect to get back. So method, condition, expected. So if I was testing distance between points, it would be test distance between points, points 10 units away, returns 10. Test distance between points, equal points, returns 0. That's the convention we follow. And if you follow that pattern, it becomes really easy to know and follow and understand what each test is doing. Very easy. So here, when I had test equals, now I know the magic method is called underscore underscore EQ underscore underscore, but typically you would say equals. So test equals on equal spheres returns true. Actually, that's not even right. Really, it's not even returns true. Should be like R equal, but whatever. Point being, maybe my name could have been a little bit more improved. Anyways, any questions so far? So there's still more I want to show you, but I'm going to skip this just for a moment, and I'm going to show you how to run these unit tests. Now, on Colab, the way we run these are a little funny. Typically, if you're doing this locally, you'd have it set up automatically to run your tests whenever you like build your code or run your code or anything. But this is how you get it to run in Colab. You're not going to memorize this. Don't worry. I always just, copy paste it. This chunk of code right here. Let's get rid of this. And when I hit run, this will run the unit tests. And look, there we go. This is what we see. It's telling me it ran all these tests and they all passed. That's good. Great. But let's go back here for a moment and here, let's make these spheres equal. Okay? This test should fail, not because the code in the sphere class is wrong, but because the test was wrong. Just to show you that what will happen if it fails. So I rerun that. Now I run it. And look at that. Test equals on not equal spheres returns false. Fail. Uh-oh, something went wrong. And it's telling me, okay, one test failed. Assert not equal sphere A, sphere B. Assertion failed. Okay, sphere, that sphere does equal that sphere. And I can see now, instead of just assert failed that you saw before with your assert tests, now it's telling me something more helpful. I realized before you could have gone and then, okay, you see it failed, so you go print out sphere A, print out sphere B. What do they look like? Are they different? I get you could tinker and dig deeper yourself, but look, it's already done for you now. It tells you. This is great. Let's go back. Make those different. And now, actually, let's go break, here. Let's go break our repr in the sphere class. So now this will fail because the code in the sphere class is wrong. I made my repr wrong intentionally. So when I hit run, look at that. Test repr arbitrary sphere returns correct string. Failed. Why? Well, sphere center point equals 0.3d x blah, 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 blah is not equal to sphere 0.3. I can see what's different. It's showing me. This is fantastic. This is so much more helpful than before. So, the last thing I'm going to want to test here is the diameter. Really, I'm going to want to test a lot more, but the last thing I'm going to show you is diameter. I want to test diameter. And here I'm writing 4 test cases, 4 unit tests for the diameter. Test diameter radius 0 at the origin returns 0. Test diameter radius 1, origin returns 2. Test diameter radius 0, arbitrary center point returns 0. Test diameter radius 10, arbitrary center points returns 20. I've got 4 tests there. There we go, great. Now you might think to yourself, okay, this feels kind of redundant here, right? There's a lot of similarity here, and you're right. And each test is supposed to be like self-contained, whatever. But there's a point where we got to go like, okay, come on, they're the same. So you might be tempted to be like, okay, look, if I do this, actually, okay, no. Instead, what we do is we do this. Now, you don't have to do this. You could do it the other way where you write out all the tests. Or you can basically add a loop. But it's more than just a loop. What's wrong here? We're using this right here, which is important. And I'll talk about why in a moment. So here's what I've done, is I've created a list with 1, 2, 3, 4 cases in it. More or less the cases I was showing you before. I think here I added, instead of 10, I made it 10.1 for the diameter, the last test, just for fun. So instead of having 4 different tests, I made a list with the 4 different cases in it. Now, mind you, the fact that this is called cases is arbitrary. I just called it cases because I liked it. Test case, right? And I have another list, expecteds. where like the indices correspond to each other's. The first thing in the cases corresponds to what I expect in index 0 of the next one, right? So I expect to get 0, 2, 0, 20.2. Okay? All right? Then here I've got 4. Now, mind you, this is some new here. It's not too bad. Don't worry too much if this spooks you a bit. When you zip things together in this context, it's like you make a list of tuples of the values from each separate list. So instead of having 2 lists with 1 value at each index, I create 1 list with a tuple of 2 values at each index. And then, when I loop over them, you know how usually with the for loop you get the 1 value out of each thing? Well, now we are unpacking them immediately into their 2 separate values. This just provides a really nice and easy syntax way to get 2 values I want to loop over from each list respectively. If you don't like this, I'll show you the more general version in a moment. So for each case and each thing that I expect, now this here is important, the with self.subtest. And I'll explain why in a moment. But then here we say, okay, self.assert almost equals what I expected, and then case.diameter. Call the diameter method on the individual case, basically the individual sphere. And then I've got this 5 here. It's probably not necessary in this particular example. But you'll notice here, remember how it's always kind of difficult to compare floating point numbers? How we always did that thing of like, well, check if the absolute difference is below some threshold. Assert almost equal is the way to do that. That's the way we do this easily. And the 5 at the end is to specify how precise we want it. I probably didn't need it on these test cases. I probably could have left it at whatever the default value was. In fact, let's see what happens if I do that. But here, there we go. And if I go run these, yeah, they all pass just fine. Great. Now, the with self.subtest is important. You could look at this and be like, would this not achieve the exact same thing if you didn't say with self.subtest? Almost. But this is like having multiple asserts, multiple self.asserts in the same function, same method, which is bad. We don't want that. We want to know if a test case fails, if a unit test fails, we don't want a lot of asserts, because if we do, we don't know which one caused it to fail. So if any one of these fails, it'll be like failed. But with this, for example, one of these should fail now. It'll still run all of those cases, but now it'll tell me which of the subtests actually failed. So this is a way of eliminating the issue of if one fails, they all fail. Well, no, now it'll just remember exactly which one failed. And it tells you 0 does not equal 220 within 7 decimal places. There's a 220 difference. That's awesome. Any last questions? All right.